Excuse me. Let's get started. Today we have Tina Brower-Thomas from Howard University. We'll be talking. It's a pleasure to get to know Tina. It's about 5 years now or something like that. She's been an integral participant, boss of sorts, for our SDC for Integrated Quantum Materials. She looks after the Howard parts of the education and outreach operation, and also the Boston part of the education outreach. She's been working with Philip Kim, traveling back and forth to visit Boston over the fall, and she'll be talking about that today. She got her graduate school degree from NYU, then went to a postdoc at the Naval Research Lab down in DC, and then moved off to Howard University.
Yep. Thank you. Thanks so much for having me. So as Bob was saying, I am, as far as CIQM, the Director of Education in the Washington area. And I really like showing this picture at the Museum of Science Boston, because I feel like it just culminates our efforts to have a cohesive center. And we have, this was taken in the summer during our first summer school, and we have a lot of participants from Washington and within the college network, and faculty, and some of the faculty's children actually came to this event. So you may know me as the education director, for those of you who are involved in CIQM. And part of that work, as Bob was saying, is the summer school. I'm involved with recruiting students, matching them up with research projects within the center, and really trying to push collaborative research within the center. And now I'm participating in one of the center activities that we provide, which is the ES-294 talk. So, and close to my heart, I have to put this slide up. This is Howard Nano Fabs in Washington, D.C., in our old building. But a big part of why I am at Howard is for education and outreach, and to integrate research and education. And so this slide is just showing some of the students from Prince George's Community College that came into our labs to learn about carbon-based materials and scanning electron microscope. These are high school students from a nearby magnet high school. So those things are really dear to my heart. But today I want to talk to you about decoration of graphene with transition metals. As you know, graphene is a big part of the research within the Center of Integrated Quantum Materials. And it has some wonderful properties. However, we have to figure out how to, there's a number of things we have to figure out. One of them is, can we induce a band gap in graphene? Can we functionalize it so that we could use it to make interconnects if it's going to be part of the electronics industry? And so I thought it was really interesting. I wanted to point out that the 2016 Nobel Prize in Chemistry was awarded in combination with some other folks to Sir Fraser Stoddart, who actually developed this molecule called rhotoxan. And rhotoxan acts as a molecular switch just by virtue of the pH that it's involved in. And so that is truly a quantum regime. So the question is, how do we get from a classical regime, which is a big part of what silicon industry is based upon, to a quantum regime? And so graphene is a part of that. So I want to show a video. I had a little trouble getting it to play in my presentation earlier, so bear with me. Actually, I think I could just click here. And it's going to go to this, because I think it's a really neat video showing how, and it's still not showing. Okay, well, go to Wikipedia and look up rhotoxan, and it will show you that you get a different conformational change when some of the functional groups are protonated or deprotonated, depending on the solvent that it's in. And actually you get, it also involves some pi-pi interactions that allow for this switch to operate. So there's a reason why I'm telling you that, but so please look at the video. It's very interesting. And so with graphene, as I was saying, it's opened the door. It's also, as you know, got a Nobel Prize of people who isolated it. But it's opened the door for research in the 2D materials area. And despite all of its wonderful properties like high mobility and high thermal conductivity, graphene lacks some special properties, particularly that it has a zero band gap. So for electronics, we've got to figure out a way to get beyond that. And so there's many schemes out there for how to functionalize graphene. Here I'm showing a fluorinated graphene where using some gas, the graphene lattice was fluorinated, and you have some varying degrees of the pi system and sp2 versus sp3 bonding. And you can see here in the Raman spectra, which is indicative of the pi systems in graphene, and that after you fluorinate it, you no longer have the signature of a graphene because you no longer have the sp2 bonding. And in brominated graphene, you can think of similarly, when you brominate, you actually replace a carbon with a bromine. And that's not what we're looking for. We want to functionalize it, but we still want the good properties of graphene at the same time. And some other ways that people are looking at is using monolayer graphene oxide and by nitrogen doping it. And that's interesting because without the graphene oxide, you can't really functionalize graphene. But with graphene oxide, there's some issues with you lose some of the properties that we want to take advantage of. So I'm thinking about, when I got involved in the research within the center, I'm thinking about how I could use my experience to actually functionalize graphene and still maintain some of its properties. And I'd love to, as many people would, engineer bandgap in graphene. But also, I would like to look at pathways to molecular interconnects for quantum device. If we're going to have this quantum device, we're going to probably have to marry it with current technology and some other technologies. How can we do that? I think that you're going to have to functionalize graphene, and I think I'm going to show you that it's possible. It could be possible to functionalize it so you can use the functionalization to interconnect graphene with other parts of some kind of quantum device. And to do that, I'm thinking about graphene as a template for hierarchical quantum structures. So in order to sell you on the idea that this might be possible, I'm going to take you back to the research that I have done previously. So a big part of my research has been in self-assembly. And self-assembly is where you have a disordered system of pre-existing components, and they form an organized structure or pattern as a consequence of specific local interactions among the components, and it's void of any external forces. So self-assembly happens on different scales. I'm showing two extremes here. This is self-assembly of logs of wood on water. And you can see one thing about them is that the logs are pretty uniform in size, and that's a big part of how self-assembly works. You're using molecules that are, or materials that are very much alike. And because of that, they want to form a crystallized structure. Now, on a molecular scale, this is called molecular self-assembly. This happens to be biphenyl thiol. And if you are not used to looking at scanning probe microscope or scanning tunneling microscope images, you may not notice it, but there is order here. There's order in the structure by making this monolayer of biphenyl thiol. So what is at the center of self-assembly monolayers is the gold-sulfur bond. That's one thing. That's one part. The other part is van der Waals interactions between the backbone of the, in the case of alkane thiols, of the alkane thiol carbon structure. And so it's well known how the sulfur bonds to the gold. It actually, you start with a gold 111, I should tell you, which is a crystallized structure of gold. And it has order, and we know the spacing between the gold atoms on the surface. And we also know what happens when you come with a sulfur atom, how it likes to grow relative to the gold surface that we're using. And this actually is showing all of that. It's showing the spacing between the gold atoms. It's also showing the overlayer structure of an alkane thiol monolayer relative to the gold surface. And this line here actually represents the orientation of the alkane thiol backbone relative to one another. And so those are all important. I think the main thing I want to show here is that there's a driving force. And the two, whenever you have a monolayer, I told you that there are specific interactions. In the case of alkane thiol, it's the gold thiol bond and the van der Waals interactions of the alkane backbone. And so how does it work? Basically, it's a chemisorption, and it's pretty simple. It's really simple chemistry. You have your gold surface, and it's a thermally evaporated gold on the surface. And then you introduce that to a dilute solution of your molecules, and over some time you get an ordered structure. Oh, I have to keep doing this. And so there's a good number of characterization techniques that are involved in actually showing that you have a monolayer. Ellipsometry, which is a relative method because it's using a difference in refractive index when you're looking for thickness. You start off with your substrate that you haven't modified. You get the refractive index of it. You modify it. The refractive index is going to change, so how it interacts with the polarized light is going to be different, and that difference can be spit out using Snell's law to give you a thickness, so on and so forth. With grazing angle FTIR is a very interesting technique as well. In that technique, you are using p-polarized light impinging on a reflective surface, and because it's p-polarized, you already know that, I should say, that vibrational modes of molecules that you look at are very distinct in their position in three-dimensional space. And it's that vibration and that distinction that helps us determine what materials we have on the surface. But now you come in with a p-polarized light. Not only are you getting information about the molecules on the surface, but you're also getting information about their orientation and the degree of order. So, so it's a very important tool for people who are using self-assembled monolayers. And with scanning probe microscope, we can get the chemical composition and also an idea of what environment the molecules that we are looking at on the surface, what their environment is. And then I showed you an earlier image. This is, tells us about order, but you can also look at IV characteristics and so forth using scanning probe microscope techniques. So this is before my time, because I hate aging myself. I hate putting the numbers up there the years. I'm just that vain, sorry. But this is well before my time. But the point here is that beyond making monolayers, people started to think about thin films for applications like in nonlinear optics and second harmonic generation and molecular electronics. And they started to think about how they can build functionalization into thin layer systems. And so one example is using dithiols with, in this case, copper 2+, to try to make a hierarchical structure. And the point here was that if you took one dithiol, you introduced it to a copper with the +2 oxidation state, it would coordinate with the two thiols and make a bond, make a alkane thiol. This is what this is called, alkane thiol, with sulfur connected to a copper, connected to another sulfur, and so forth. And one of the ways we figured out whether this would work or not work is to look at the oxidation state of copper. Because if copper is in the proper oxidation state, we can determine its coordination with the sulfurs. In this case, we discovered that it's actually not, you shouldn't say in experiments it's not what we want, but it really wasn't what we wanted, or they wanted, because I wasn't there. But what they found is that you actually form what is called intralayer disulfide bonds here. So, which is very interesting. But how is it possible with the alkane thiol? I should say just some properties about alkane thiols. Each fold here, there are not any chemists here? No? Okay. So this represents a carbon chain. And relative to the molecules I'm going to talk about next, there's a lot of, you can almost think of it as a spring. There's a lot of flexibility there, okay? And so the question is, given the atomic structure of the gold 1,1 surface, how is it possible to get the disulfide bond? Well, the disulfide bond has a bond length of about 0.25 nanometers. But if you look at how the alkane thiols arrange themselves on the gold 1,1 surface, there are some possibilities of where the disulfides could actually, or the disulfides could meet each other. But those possibilities are larger than the disulfide bond. So because of the flexibility in the alkane thiol backbone, you can actually get the molecules to, they're associated with a bend and a rotation, but also with some flexibility, and so you can actually get a disulfide bond. So, oops, did I go too? Okay. So with that in mind, and again, the idea of molecular electronics was starting to percolate about the time that I was entering graduate school, and I think it really was because people, well, there's a lots of reasons, but one reason that, so let me say this. This guy, these two guys, Avram and Ratner, proposed in 1974 that functionalized aromatic molecules could be used in the construction of electronic devices. So there was here I'm showing, I'm sorry that it's so small, but lots of different electronic molecules. People were synthesizing molecules like polyaniline, polythiophene, and that may not mean much to you, but it's basically a lot of harsh solvents, a lot of in the lab, you know, nobody wants to do that. Like, it's just not a lot of fun, in my opinion. but in some pretty circuitous routes to actually getting this functionalization that was proposed in 1974. But at the same time, I think that methods to evaporate gold on surfaces started to improve, and you could get crystallized gold, and you could start thinking about epitaxial growth and stuff like that. And so people were taking different molecules and actually making the thin film. So I think those two things came together kind of around the same time. But so now I told you that you have the aliphatic thiols, and they could form this interlayer disulfide bond. But if you get to these rigid molecules, some of which people had already started thinking about what their electronic properties might be like, and see whether you could put those on a surface and start making a multilayer, then it becomes a different question. There is some flexibility, but not nearly as much flexibility. Here I'm showing just the torsional, what's the word I'm looking for? Rotation between the two benzene rings here. As you can see, there's an angle relative to each other here. So there's some degree of rotation, but one of the things that you have to keep in mind is this is a much different beast, not only because of how the bonding, but also the amount of space that they take up. It's just not, it's just a different scenario than an alkane thiol monolayer. But what they do have in common is the gold S bond that's formed, that there is order when you make a monolayer, and that unlike the alkane thiols where you have van der Waals interactions, in this case you're looking at pi-pi interactions of the benzene. And there's a known angle associated with the molecule. So I went out to look at how I could use molecules like biphenyl dithiol to make a multilayer in this way, hoping that I can make the copper sandwich, because I was hoping for, if you apply some voltage, that you have electrons flow through here, through the sulfur, through the full d orbitals of copper, connected to another sulfur, and so forth. And that eventually, depending on what molecule I chose to put in this system, I can build in functionality. So one of the things you have to look at is, like with ellipsometry, you kind of have to have an idea of what your thickness is going to be, taking into account the angle that you expected to make on the surface, whether this is a surface normal, and think about how much time and what the concentration you need in order to make a monolayer. One of the reasons why that's important is because this is two thiols. There's a thiol here, that's what we call the free thiol, and there's a thiol here that is on the, that would be bonded to the gold. But they can also bind to each other to make a disulfide bond. So that's why we do it in nitrogen, and we take a lot of care about how much time and what the concentration is, hoping to drive the gold S bond as opposed to a disulfide bond on the surface. And so most of the methods that I showed you for characterizing the material are what we call relative methods. It's relative to something. It's relative to a previous refractive index. It's relative to some other orientation on the surface or what have you. But the one thing about using scanning probe microscope is actually a real, like a definite, like it's either there or it's not. It's either this height or it's not this height using scanning probe microscope. So at the time, nano shaving was kind of a newfangled thing. And what that is, if you if you come in with a monolayer on a gold surface and you have an AFM tip and you apply the correct amount of force, you can actually shave away some of the molecules, and then you can go back and with your cursor look at the difference in height between the hole that you made and the monolayer on the other side. And of course, like I showed you earlier, that you can look at, you know what the gold structure is because that's well characterized by STM. So you know when you hit the gold versus whether you're still in the monolayer, you can get an actual height measurement. And so that's important. Here I'm showing some FTI, grazing angle FTIR data, which, as I mentioned earlier, is very sensitive to the orientation of the molecule on the surface. And it tells us something about the degree of order. And so as you increase the number of layers, which is what I'm showing here, this is actually what we call we actually made this in solution as well and looked at the Raman spectra of that, thinking statistically. I'm not going to get into those details, but just keep in mind that the relative shift from this 1470 peak is giving us some idea about the order within the multi-layer system. And also, if you look at the relationship between the number of layers and the absorbance, we can see that it's a linear relationship. And also, the thickness is also a linear relationship. And the number of layers, the thickness corresponds to the number of layers based upon the size of the molecule that I described to you earlier. And furthermore, using the nanografting or nanoshaving technique, this is the thickness measured by AFM of about 4 nanometers, which one molecule is about 1.32 nanometers in size. So taking these things into account, we're pretty confident that we're making a multi-layer system. Other techniques that were used, we want to look at the roughness of the surface. You always want to know, at this time, people weren't really that good at getting aromatic systems to form the same kind of ordered layers as they did with the aliphatic systems, the alkane thiols I was telling you about. So looking at the roughness was about as good as you could get to understanding that. Here you can see this right here is actually a gold terrace. If you can see that right there. And this is a monolayer. And if you go across this monolayer, you can see the roughness. And you can also, we measure the thickness. And as you continue to make multiple layers, you see that the roughness does increase a little bit, but the thickness is still on par with the number of layers that you expect. And you can also see that the gold terrace kind of disappears, which is actually just means that I'm growing more and more layers on top of the surface. This actually was done in situ, and so we're actually looking at the same spot over time, and then going back and looking at the thickness. So we take our molecules, we have them in a liquid cell, we pass the molecule that we want to make in the monolayer through, add the connecting atoms, and continue to repeat the process until we actually get the multi-layer that we're looking for. And then using techniques like nanografting, where you actually come in with a molecule, a different molecule, where you know the size of that molecule, and you either make a hole in the layer that you're looking at, and then backfill it with the layer that you know the size of, or vice versa. And then you look at the relative height between the molecule that you know versus the molecule you're trying to investigate. And you can actually use that as another backup to proving that you have the number of layers that you want. And these techniques were fairly new at the time, and they actually came into play later, and I'll show you that. And so again, looking at XPS, I found that I do not have the sandwich model that I was looking for. It was a little disappointing, but it was fun. I did make the multi-layer, and I found that I actually made, instead of intralayer, where the two sulfur bonds have a disulfide bond this way, I made interlayer disulfide bonding. And I know that because as I look at what we call a trilayer, and a trilayer with copper on top, I have two different, so this is a sulfur region in XPS. I have two different sulfur peaks, or two different sulfur species. This is looking at the p orbital, so it's some splitting there. So you get a doublet. So one doublet corresponds to a thiolate, and another doublet corresponds to a free thiol. And if this was a copper sandwich model, I would expect that I would have basically all thiolate, but I don't. So that's how we knew that we do not have the copper sandwich model, but we have a multilayer. So with that in mind, I sought to look at other systems that I could come up with, and this was basically, the challenge I put forth for myself is, can I put different types of molecules within a multilayer system? And in this case, the simplest one that I thought would be easy to prove that I have would be looking at aromatic systems versus aliphatic systems within a multilayer, because in particular, their IR signatures are very distinguishable. So in this case, you have the aliphatic system. This is a grazing angle FTIR sample of 3 layers. And you can see that I'm sorry, not 3 layers. 3 layers. It's this one right here. You can see the aliphatic, vibrational asymmetric and symmetric stretching of the carbon backbone. And you can also see peaks that represent the aromatic system all in one spectrum. And then, of course, I always have the ellipsometry and so forth. And the thickness corresponds to the number, exactly to the number of molecules that I put in. And by XPS, we could easily look at, again, the sulfur region. Here I see both the thiolate and the unbound sulfur. And there is copper present. And there's actually 2 different carbon species. There's the aromatic carbon species and the aliphatic carbon species. And taking all this together, specifically looking at this oxidation state of copper, I think I didn't say that. Did I say that? I'm seeing copper in +1, by the way, right? So, okay. So this is what we propose is the final structure that we came using this methodology. So beyond that, I thought not only can I look at different molecules, but how about looking at different atoms as connectors? And I was interested in transition metal atoms that like the +2 oxidation state. And I also thought about the periodic trend and looking at their redox potentials. I thought it would be nice to show that fundamentally, if you just look at the periodic table, you would not expect these to make a multilayer, because the redox potential does not lend itself to oxidizing the sulfur to either a disulfide or just as a catalyst or a connector between the 2 sulfurs. But you might get somewhere with mercury, and we already knew we could get there with copper. And so I'm not going to bore you with all the details, but I will say that the periodic trend, they got it right, the guys who came up with the periodic table. So we saw that with copper and mercury, we could get a multilayer. If you look at using XPS, we also looked at the relative concentration of the different metals within a multilayer system. And we found that, that basically after the first layer, cadmium and zinc are not incorporated into multilayer. However, mercury is, and you start to see a drop-off, which I think is probably due to attenuation as you grow the number of layers. And so the XPS results, again, show what's unique about mercury. Again, we get the multilayer, but we see 2 different mercury species. We see mercury 0 on the first and second layers, but then after the 3rd and 4th layers, we see actually mercury 2 oxidation. And so I'm still interested in figuring out what that's about. I'm still fascinated by that finding. So moving on, people were thinking, okay, it's great we can make, we have these different molecular components. They were at this point well characterized. People had structures for diodes, for switches, and for wires. The question then became, how do you get that into some kind of structure or network that you could utilize? And so in my postdoc, I joined this group and worked on this project where we proposed to take a virus, and the virus itself is self-replicating, right? one virus, unless it's mutated, one virus of a kind looks like another virus of a kind, which is ideal to actually make a network by self-assembly of viruses. Now, what if you can make a network of viruses that are 30 nanometers in size that were actually wired with some of these functional molecules? So that's what we set out to do. And so we started with a CalP Mosaic virus, and I shouldn't say we, Scripps Institute gave us this. But so they mutated the virus. We worked at that time with 2 different mutations, and the mutations basically put thiols on the surface of the virus. And so one mutation we decorated with 5 nanometer gold nanoparticles, and another mutation we decorated with 2 nanometer gold particles. And the places where this was mutated, we understood it very well. And we also understood what molecules we wanted to use and what functionality we wanted to put on the virus. And so having 2 mutations allowed us to come up with 2 different types of what we call virus nanoblocks. They were, in a sense, wired differently. And it also allows us to have somewhat of a control to see what was going on. And so this is more about how it was mutated. But one of the things that yes?
With the virus, can it still, when it has to go stuck on the surface, can that still infect somebody?
So it's a P virus. So it's for Ps. It can.
Oh, they infect the Ps?
Right, yeah.
But it still goes, or that's...
That's not something we tried. But one of the challenges I will say is, like, how do you, if we don't keep the virus looking like a virus, even though we do all this stuff to it, similar to what I want to say about graphene, if we don't keep it looking like graphene, it won't work, right? Because so we had to be very careful about what solvents we used, the process by which we decorated it and isolated it, and we were able to get an intact virus in the end. But whether or not it would still act as a virus to Ps, we didn't explore that at all, yeah. But that's the analogy that I'm eventually trying to make. Here we had to figure out how do we, because we want to do what I described, but we also want to come out with a virus that still has its main structure that we could then self-assemble, okay? So one of the things that we did, so the big part of my job was actually, I helped out with different parts, but the big job was actually how do we wire it and how do we prove it's wired, and then how, after it's wired, how do we get in a situation where we can test it? And so one of the things that we used to look at whether it's intact is the tryptophan signature at the 290, the emission of that signature, fluorescence emission at a 290 excitation. And that's important. I'm going to go back to that. But this is the process that some very talented biochemists that worked in our group, it was very much an interdisciplinary group, worked out. We all worked together with thinking about solvents and different things like that. It sounds simple, but it was not simple. But essentially, we tried different methods to actually decorate it and then separate it. And we ended up settling on this electrophoresis method, where actually we took, after we got the gold particles on there, we put it in an electrophoresis gel, and actually over some time and applying a voltage over some area, we actually were able to separate a decorated virus from free gold nanoparticles. And we knew that because we could then once we saw the separation, we just cut different bands. And we could figure out like which band has what. Mostly using, in terms of the virus, using this signature of the tryptophan. And so then we had to wash it and make sure that we got rid of all the free nanoparticles. And then looking at tunneling electron microscope, here you can see a model of the mutated viruses. This is the 5 nanometer gold virus, decorated virus, and this is the 2 nanometer gold decorated virus. And looking at the TEM, you can obviously see where the metal is located, and it matches very well to the models that we had for the virus. In this last image, you can actually see this one was actually wired, and you can see a signature of the molecules showing up because they are conductive in the TEM image. So that would be nice, right? So what are the molecules that we're talking about? We used, depending on which virus we mutated, we used a for short, because it's a really long name. You see all these functional groups? So let's just call it diplatinum, and BPDN, which is actually acts as a switch, and then OPV, which acts as a wire. So one of the ways I proved that I had not only the virus, but the virus and the virus. So once I got my little solution, right, I have now my virus that has a gold nanoparticles on it. I had to come up with a way, find the right concentration, the right solvents, the right perturbation or lack of perturbation, mixing to get the molecules on the surface. And then I had to say prove that they were actually there. And so fortunately, in one case, the molecule signature, in particular OPV, has an emission spectrum at the same 290 excitation spectrum of tryptophan. That's the beauty of these aromatic systems. They have some fluorescence emission that is, going to be on the same excitation of the virus, because the virus has a lot of functional groups that very much look like the aromatic systems, right? So now this was done for all the molecules, but I'm just showing here that at a 290 excitation, the emission spectrum of a virus by itself and the emission spectrum of a virus that has the molecules on it. Yeah. You have to consult the patent. Yes. So this was actually patented. Just a little, well, it's already patented, so I guess I could tell you. We're still talking about a gold S bond. And we're talking about a gold S bond. We're talking about two thiols, right? It really was just a matter of finding the right concentration so that you didn't end up with an entangled mess, right? And the right conditions, like under nitrogen and so forth. And then the hardest part was wasn't that bad. The hard part was separating the virus with the wires on it from just what didn't come out in the wash, so to speak. And just being very careful about that. So, but basically it was just finding the right concentration. And this is truly self-assembly, right? And in the end, it didn't matter whether I had I'm showing here one molecule. I don't really think it's one molecule, right? It's just the path of least conductance, right? So it's probably several molecules here. But I thought about like the area of the nanoparticle and the size of the molecule, how many I expected to be on there, and then from that thinking about what the concentration needs to be, stuff like that. Yeah. So okay, so now here's the proof. So this is actually showing. So this goes back to the nanografting and nanoshaving that I told you about, and the backfilling and all that stuff. So using some of those techniques, we could actually take an alkane thiol monolayer and put a molecular wire here that we want to investigate. I should mention that there's a lot of stuff in literature about what's really going on in these molecules. Are you changing the structure of the molecule? Is the test bed correct? There's all kinds of questions at this time about how, whether what we think we see from the IV characteristics is really a function of what we think it is. And so there was a lot of controversy about how do you actually make the right test bed to measure the material you want to measure. So in this case, so that's just some background to show how important coming up with this kind of structure that actually works was. So you have the monolayer here, you put a gold nanoparticle on top of the wire, and of course, this is idealized, right? So it's not like, there might, somewhere near here, there's another one, right? But you gotta look in the STM, take an image of it and then come back and say, okay, this is where it is, and now I'm gonna put my tip here, right? So here we actually see, this is the signature of the, in this case, the wire. And this is the signature of a switch. So as we bias, we get to a point about 1.7 volts where the current increases, conduct increases, and then as you go back on the bias, it comes down. So this is actually showing switch behavior. That's a function of, where's that molecule? Of what's happening with these nitrogen groups on the on the backbone of that aliphatic system. And so here we have a wired virus nanoblock that was put in a similar test bed situation. And this virus was actually decorated with both a wire and a switch. And you can see both behaviors in the IV characteristics. So it's some steric, where is it? Get confused. So there's a conformational change as you apply the voltage. So there's a different kind of switches. There's stochastic switching and voltage-induced switching. So I'm showing voltage-induced switching. When you change the voltage, you get a conformational change. And that conformational change is a point where you can actually have sort of like the free electrons sort of frozen in a certain conformation. Then if you go back on the voltage, they are released. Yeah. So, so now that I've convinced you or shown you that you can do really fantastical things with a little bit of, with some metals and some different molecules and the right characterization tools and so forth, I'd like to see how that can bear upon putting quantum structures on top of graphene. Now, what I should say about this is I'll readily admit that graphene is nothing like a virus, right? There's not a whole bunch of functional groups. There's not a lot of, the chemistry is pretty boring, so to speak. There are limited chemical routes that will actually allow you to, like we still had the virus intact with the molecules on it. There's limited routes to have graphene be graphene and still be functionalized for the kind of engineering we might be interested in doing. But what it does have is a pi system with delocalized electrons. And so I'd like to utilize that pi system thinking about some of the same atoms that I'm used to working with, like copper and mercury, and think about how I could use pi cation interactions, which are electrostatic attraction between a cation and a pi electron system, to functionalize the graphene. Okay, so this is actually recent work showing that, well, somewhat recent work showing that copper-2 was theorized to have some. It's a big part of some biological function, but it was theorized that it's stabilized by pi cation interactions. And also, there's recent work that copper-1 is also stabilized by pi cation interactions. So the question can be, can we utilize a difference in redox potential or between metals, or the difference in a copper-2 state versus a copper-1 state for something on graphene? And then can we create an environment around the copper that helps stabilize the copper on a graphene surface? So some theoretical studies about atoms on graphene go like this. There are basically 3 areas that people look at for where the atom would occur. One of them is here, which is called the bridge site, which is in between 2 carbons on a for lack of a better word, a benzene ring within the graphene. The other one is what they call the hexagonal site, which would sit right in the center of the pi system of a graphene. And the other is what they call the tetrahedral site, which sits above the carbon atom of the graphene. And so why I'm interested in these metals, because I like the fact that there is some kind of interaction, but it's not a covalent bond. It's not like the borine or the fluorine where you're substituting a carbon for another atom. But there are a lot of questions about how you can get it there, how is it going to be stabilized, and that's what we're going to be after in this collaboration. I want to mention of a colleague at Howard, Dev, who's a physicist that does, she does some theoretical work. And forgive me, Dev, if I don't do you justice, but I just wanted to point out that she's done some work with looking at metals on graphene and how they're stabilized. And one of the things that she's thought about is how you can basically put defects in graphene and then use those defects as sort of like an anchor to stabilize different metals. So I think that's an interesting approach that we're going to be looking at. And so where are we now? We're hard at work. This is a collaborative project. Mehdi is here working with Philip Kim and learning some of his techniques to help move the project forward. So I'm just going to show you some preliminary data. We're a little reluctant to say, oh yes, we have, we have like, true evidence of a band gap or a doping of graphene, because there's a lot of work to be done, and graphene is very sensitive to its environment in terms of doping and so. So we want to be thorough, but I will say that some preliminary results show that here you can see this is pristine graphene. I will say this is a sample that was created by CBD and transferred to a silicon oxide layer. But nevertheless, this is showing before exposure to in this case, we're using mercury, that afterwards we have a shift in the wave number to an actual higher wave number. And according to some theoretical studies, that's indicative of p-doping or hole doping. As you go higher in the wave number, particularly at this 2D peak in graphene, you actually, that's indicative of hole doping. So I'm reluctant to say, but hopefully we've possibly could have changed the Fermi level, the energy of the Fermi level by hole doping. And so right now we're really looking at chemical doping techniques. We like to consider possibly some of the work that I described by Dev in combination with that. And so using XPS, this is a, excuse me, this is a scan of the XPS showing all the elements that are on the surface. And we can see here that we have the aliphatic carbon. This is after decoration. And we have the signature for mercury. So the concentration, I admit, is relatively low, but we're repeating the experiments, and we've shown different concentrations of mercury and copper on the surface. So we have a lot of work to do. Looking forward to it. And I think, though, with the collaborative effort with Philip Kim's group, we're working on decoration methods, characterization tools at CNS. We really would like to see an atom where it might be on the graphene lattice, and I think there are lots of tools in CNS that can help us do that. And we're looking at different type of ways, test beds, to actually look at the characteristics once we actually get the molecule on there, and a combination of theoretical studies. I think that with a little bit more time, we could, complete this paradigm of using simple chemistry and great characterization tools and elucidate a structure like that. And then, well, I won't say, but there's further chemistry that could be done here, which I think is a good, interesting idea to think about. Okay, so any questions? Thank you.
What's sitting on your graphene by studying transport or doing some sort of light scattering. So I'm envisioning have some virus, another virus, one binds. Can you tell the difference or something like this?
If I have a virus on the...
Could you somehow distinguish between different viruses, for instance?
I guess if you know well enough, there's a lot of diffraction information, X-ray diffraction information on various viruses. So I don't see why that wouldn't be a problem, especially since graphene is transparent. So I think that's an interesting idea. I don't see why it wouldn't be possible if you just look at some different diffraction patterns of the virus.
I guess by studying some properties of graphene, like transport.
I haven't thought about that. I mean, I guess my first inclination is that, I don't know, I have to give that some thought. But I guess you can always look at the difference in the Raman spectra. You can look at the IV characteristics and see if that changes. Yeah.
I just want to follow up on Trevor's question.
Mhm.
Has there been work on using graphene as a sensor for different types of viruses?
I don't know about viruses, but people are looking at graphene in general as a sensor. Yeah.
That I know, just tailored specific toward viruses.
That would be interesting. I think the fluorescence spectroscopy is such a great tool because you don't need a lot of material, and you don't have to have high concentrations of material, and also it doesn't damage the surface. So I think probably using fluorescence would be a good way to look at that to see if you could use it as a sensor.
Maybe we need to chat with some biochemists.
Yes, maybe so.
Other questions? I guess I have one.
Yeah.
Do carbon buckyballs stick, or do they bounce off?
Bounce.
Sort of similar stuff, only it's in a shell. And with that actually, it sort of matches up in the spacing and all that.
Do they stick on to?
Yeah, you spray some buckyballs on there.
On graphene?
Lock in, yeah. Or do they not stick at all?
I haven't looked at that, but I think be interesting. I think a theoretical study of that would be nice. Yeah.
Okay, well, any last question? If not, let's thank Tina again. Okay, and students, this is the last lecture, and actually the last day of classes is tomorrow. And so you need to sign in here if you haven't.